what are aromatic compounds? Aromatic compounds are molecules that have a special ring structure like benzene. They are very stable because of their unique electron arrangement.
So this video tutorial is all about aromatic compound. Basically, we're going to look at the 4 characteristics that make a compound aromatic and how can we apply this to an example and to determine whether or not it is a specific aromatic compound that's fall in aromatic bracket. So if we were going to look here, we have the 4 basic rules that make a compound aromatic. So firstly, it has to be cyclic. So it could be a 6-membered ring or a 3-membered ring as long as it is closed cyclic. Then the second thing, it has to be conjugated. So later on, we will be discussing what are the characteristics of a conjugated compound. So let's proceed to the third thing. So it has to be planar. So any or all of your compound involved in a cyclic component of your structure, even if it's a bigger structure, must have to be sp2 hybridized, which have double bonds. And then the fourth and the final piece, it has to be odd number of pi-cloud electron pairs. As I have said earlier, we're going to discuss the characteristics of a conjugated compound. So it is a conjugated compound if it has double bonds, single band, and double bond. So we provided an example here. So in here, we will start numbering here. This is your number 1, 2, and number 3. So as we see there, number 1 contains double band, number 2 contains single band, and number 3 contains double band. So it is a conjugated compound. So number 2, it is the second characteristic. So it is a conjugated compound. It contains double bond, single band, and a positive charge. So here in the example, as we can see here, we start numbering here, your number 1, which contains double band, number 2, which contains single band, and in the third number, it contains a positive charge. So it is a conjugated compound.
So the third characteristic of conjugated compound is we have here double bond, single bond, and negative charge. So for the example, the first number has a double bond, and the second number has a single bond, and the third number has a negative charge. So this is considered as a conjugated compound. So next is we have here double bond, single bond, and double pair. So the example is the first number has a double bond, and the second number has a single bond, and the third number has a double pair. So remember, if the lone pair is in the inside, it is considered as conjugated. But if it is in the outside, it is not considered as conjugated.
So this time, we will now identify whether these compounds are aromatic or non-aromatic. So we can see the first compound here, it meets the first criteria and it does have a cycle in it. Second, it must be conjugated. Since the compound contains double band, single band, and double band. Third, it must be planar. So we can see that all the carbons here participating are sp2 hybridized, so that would mean that they are planar. So remember, that the carbon here, which is sp3, does not affect the aromatic since it is not directly part of this ring. So lastly, fourth, it must have an odd number of pi-cloud electron pairs. So we have here 3, and it makes the third rule. So this means that this is an aromatic compound. So next, the second compound, we see that it does not meet the first rule, and it is not a cyclic organic compound. So mathematically, we can say that this is a aromatic compound. So, if we take a look at the third compound here, we see that it means the first compound, it is conjugated. The third compound, it has to be planar. So, if we take a look all the carbon that are participating in the cycle, here are the sp2 hybridized, which would mean they would be planar compound, and it could be called anti-aromatic compound or particularly unstable. So, this definitely not fall on aromatic compound category. The second criteria, it has to be conjugated. Since the compound contains double bond, single bond, and lone, the third criteria, it has to be planar. So if we take a look, all the carbon that are participating in the cycle, here are sp2 hybridized, which would mean they would be planar. The fourth rule is that we need to have odd number of the pi cloud electron pairs. So that's how to apply the rules to understand whether or not aromatic compound.
Now, let's tackle why aromatic compounds are special. So, unlike normal alkenes, aromatic compounds do not easily undergo simple addition reaction. Instead, they undergo substitution reaction. So, one of the most common reactions of aromatic compounds is electrophilic substitution reaction. It is one of the most fundamental and unique reactions of aromatic compounds. And in typical organic chemistry, we cover three of them. So those are halogenation, nitration, and sulfonation reactions.
And now let's start halogenation of aromatic compounds.
We see that we need halogenation. I'll be using chlorine here and another species. Aluminum chloride is a catalyst that we need to make a electrophile, and a catalyst is not going to be consumed on this reaction. So once we start working mechanism that this reaction will have to make sure we will originate that.
The first step of halogenation is formation of the electrophile.
And while chlorine is electrophilic, it is not electrophilic enough to tackle aromatic ring and disrupt aromaticity. So this is where aluminum chloride come in. Many metal halides are good Lewis acids, meaning they're good accepting electrons. Aluminum chloride is exceptional Lewis acid. So if you pull the chlorine toward itself to steal some of its electron density, this will yield a new complex between the chloride molecule and aluminum. And because chlorine has provided some of this electron density to make this bond, the new bond that we have between aluminum and chloride over here make chlorine very electrophilic because it is now electron depleted. In this step, our newly made electrophile attack the aromatic ring. Notice that it is this attack. It's chlorine atom on the edge of the molecule over here that actually doing the attacking and not the one for formal positive charge. So that attack goes from the aromatic ring on the edge chlorine and that breaks bond between our chlorines. This attack results in the formation of our resonant is stabilized carbonation intermediate or the sigma complex if the other that name better. And finally, we're going to restore their aromaticity by removing the proton from our carbon cationic intermediate, and as a conjugated base, we're going to use leftover of our catalyst that now has an extra chlorine atom. That gives us the final product, chlorobenzene in this case, and the regenerated catalyst along HCl, which is the core product. we don't really care about this part, and as a matter of fact, you're probably not even going to mention that when you are writing the mechanism, and likewise the catalyst will remember that the catalyst still exists and we originated. But we are probably not going to be showing that in the final mechanism for the test purposes or anything like that.
So next is the nitration of aromatic compounds. In the general scheme, we can see here the main reagent, which is the nitric acid over here, and sulfuric acid, which is the catalyst. In the previous case, the nitric acid is not electrophilic enough by itself and cannot tackle the aromatic ring because it needs a little help to become more electrophilic. So here is the first step formation of the electrophilic.
And sulfuric acid is a stronger acid with the nitric acid. The reaction starts by proton transfer from sulfuric acid to the oxygen of nitric acid. This forms a rather unstable protonated nitric acid, which quickly undergoes the leaving group dissociation, giving us the nitronium ion, which is going to be our electrophile, and as the nitronium ion has a strong electrophile, it will have no problem attacking aromatic ring, making a resin and stabilized carbonation, just like we've seen in the previous case.
Step 2 is electrophilic attack.
Next step is once we have our carbonation intermediate, the last step on this reaction is the aromaticity restoration via the proton transfer like in the previous case. Again, and here we are going to be using the conjugate base left over from our sulfuric acid, which is going to be regenerating our catalyst H2SO4 over here and giving us the final, which is nitrobenzene.
So the third step is restore aromaticity.
In this case, nitration, by the way, is a very aggressive reaction, and we never want to perform it on a sensitive in a very complicated molecule. The nitric and sulfuric acid together can pretty much eat just about anything, so many functional groups may be destroyed in this reaction if we are not careful.
So this time, I will now discuss the steps of sulfonation of aromatic compounds. So step 1, formation of the electrophile.
In this reaction, we are going to treat our aromatic molecule with a fuming sulfuric acid, which is a solution of SO3 in concentrated sulfuric acid. This mixture is the thick, viscous, yellow-brown liquid, and because of its consistency and because of how it looks like, it is sometimes called the oleum acid. As always, we are going to start our mechanism with the electrophile formation.
Step 2 would be the electrophilic attack.
And in this case, it's going to be the protonation of the SO3 by sulfuric acid. This gives us the electrophile that will then attack the aromatic ring. Again, here at the SO3 by itself, it is not strong enough to attack the aromatic ring, so we need to take it over the edge by protonating it.
So step 3 and lastly would be the restore aromaticity.
So finally, we are going to restore our aromaticity by removing the proton from our carbocation. In this reaction, we're again going to be using the sulfuric acid conjugate base for this purpose, and that yields us our final product, the sulfonic acid.